Welcome everyone to Horizon Solutions this morning, and thank you for attending our latest webinar series. Today's topic is Safe Stopping Explained, hosted by Horizon Solutions Automation Specialists Chris Williams and co-hosted by Joe Amarise and myself, Andy Lucier. We'll ask today that if you have any questions throughout the presentation, that you post them to the Q&A function of the meeting organizer here, located on the bottom banner of your presentation screen. Please do not use the chat for questions. We won't be monitoring that, and we quite frankly don't have a way of logging them from there either. We will review and answer questions at the end of the presentation with as much time as allows. During the presentation today as well, we'll be posting a few polling questions, just to kind of gauge the audience and things. We will be recording this for future references for you guys, and the presentation materials will be made available to all attendees. And with that, I will turn it over to Chris Williams.
Thanks, Andy. So just to review what we're going to cover today, we're going to start out discussing what you actually need to know before you begin even sizing or implementing a safe stopping solution. Then we're going to review what the safe stopping categories actually are, followed by how to implement those safe stopping categories. Then we'll discuss a couple application examples, and then we'll be on to our Q&A. And as Andy said, make sure when you have any questions, you're submitting them through the Q&A function in Zoom. You can look for the button shown on the right of this slide and submit your questions there. So what do you need to know before you begin a safe stopping application? Well, the first thing you need to know is the safety rating that you have to aim for, and this will be based on a risk assessment. Risk assessment can either be conducted by yourself, or you can use a third-party service like Rockwell Automation to conduct the risk assessment for you. The next item you need is the application specifications. Items like speeds, loads, and the mechanical components of your system should be known if you're designing a new system from scratch, but if you're upgrading an existing system, you may have to do a bit of homework to determine these separately. These are all going to be very important to figuring out, especially your safety rating, but also how to actually implement the safe stopping properly. The third thing you need to know is how the process actually works. You need to determine when and how a machine operator interacts with the machine, what might happen during an emergency stop situation. And once you know all these items and you start implementing safe stopping, it'll actually help improve the safety and productivity of your machine and potentially make it easier to recover from emergency stop situations. So as seen on the previous slide, when you do a risk assessment, you're going to be given a PL, a SIL, or a CAT rating. These are very important to actually determining what is needed and how to implement your safety systems. So what exactly is a performance level? It's based on the ISO standards and the severity, frequency, and avoidance probability of any hazards in your system. The ISO standards of performance level also take the implementation and devices into account when giving you a category similar to PLD Cat 3. This means you cannot just use any cheap sensor in your safety circuit and expect it to meet the ratings. The performance levels are rated A through E, with E being the highest level of risk. And once the performance level has been determined, the hardware that implements the defined performance level is classified into 5 categories, which would be B through 4. The most severe risk and highest level rating is PLE Cat 4. When looking at Rockwell hardware, it's rated to a minimum level of PLD Cat 3. This means that if you use the proper hardware from Rockwell, you'll be able to achieve at least a PLD Cat 3 in your safety system. So what is safety integration level? It's very similar to PL, but this is based on the IEC standards instead of ISO standards. The severity risk, the risk level in a SIL application is based on the severity of harm and the probability of occurrence. And when these numbers are combined, you're given a SIL level of 1 through 3, with a SIL 3 being the highest level. If you have an application with the highest level of severity, which would be death or losing an appendage, then you're going to always require at least a SIL level 2. Thankfully, Rockwell's minimum level for their hardware is rated to a minimum of SIL 2. So what exactly is a risk assessment? It's a systematic process of evaluating the potential risks that may be involved in a projected activity. Best-in-class manufacturers view safety as an opportunity to invest in a proactive program rather just reacting to regulatory agencies, accidents, or worse, a tragedy in their facility. A proactive approach to safety can help you optimize safety, performance, and productivity in your facility. And as we mentioned earlier, Rockwell can perform risk assessments for you with TUV certified safety professionals. So when looking at the options available from Rockwell to do a risk assessment, we have a couple options available, either the standard risk assessment or a team-based risk assessment. Both of these options will deliver a report that includes photographs of identified hazards, an evaluation by a certified Rockwell engineer, and a full report. The standard option requires little involvement on your end because it's done just by the Rockwell engineer. It still gives you a fully detailed report at the end. The team-based risk assessment also includes basic risk assessment training, hazard identification during setup and operation and maintenance, and is done in a combination with the Rockwell automation engineer, as well as your operators, engineers, technicians, and other plant personnel. The reports will also include a view of the machine layout with improved safety recommendations, limits of the machine, accident history, and can satisfy the risk assessment requirements of agencies such as OSHA and ANSI. So we're going to take our first quick break right here for a polling question that Andy is now going to read off.
Yes, so we're going to post out a question here. Have you ever performed or been involved with a risk assessment? So if you guys could take a minute to submit your answers. We'll post that now. The voting is fast and furious. This is good. Just give it a few more seconds. Looks like we got about 85% of us have chimed in. So I'll go, in the interest of time, I'll go ahead and end the polling so we can post this. And there are your results, Chris.
All right, thanks, Andy. So it does look like the majority of you guys have been involved with the risk assessment, which is good to know. All right, so what exactly are the safe stop categories? So the three categories are derived from three different sets of standards, ISO, IEC, and NFPA. Thankfully, these three standards are closely harmonized to avoid any confusion. This means that the definitions are essentially the same in each of these documents. The three categories are broken down into 0, 1, and 2. Category 0, which is similar to just pulling the plug, is also known as safe torque off and is one of the most common implementations. Category 1 brings the load to a controlled stop before pulling the plug on the power. This is also known as safe stop 1. Category 2 brings the load to a controlled stop, but then maintains power and control over the load. And this is known as safe stop 2. So a category 0 stop, as I mentioned, is often the simplest and easiest to integrate. It does not require any feedback from the motor. So if you're using something like a PowerFlex drive, it's easily available without any additional add-on cards or additional hardware on the motor itself. It allows for quick setup for a high performance level of safety when the system has low inertia and low speed. Because this stop category only removes power without doing anything else, you can run into issues when you have high inertias or high speeds because the load can actually coast to a stop. Because of this, we see that just using a category 0 stop is oftentimes overused in industrial settings because it's so easy, but all the variables are not typically considered, and a lot of these applications should probably use a category 1 stop instead of a category 0. To make an analogy outside the industrial setting, it's like trying to bring your car to a stop by just shutting off the engine. Yes, it might work well and avoid hazards in certain situations, but you wouldn't want to do this if you're trying to avoid an accident on the highway. Something like safe torque off is always useful for applications like fans and pumps where you're not going to have a lot of hazards present. So category 1 stop, as we mentioned, is also called safe stop 1. And this is the category of stop we will want to use when the load can coast after power is removed. By using the category 1 stop, we can actually help decrease stop times and reduce machine footprints by being able to bring our light curtains closer to hazards because we can come to a quicker stop. This also can be used in an emergency stop situation because we enter that safe torque off state after motion has ended. This does require additional hardware, however, the main option being a feedback device on the motor. We will also need a compatible drive that either has an option card added in or the features built into the drive itself. In order to get a PLE rating for a category 1 stop, we'll also need a secondary encoder on the load. A category 1 stop, to go back to our car analogy, is like using the brakes to bring your car to a stop before turning off the engine. Obviously, if you're trying to avoid a hazard or an accident, this is going to be a much faster and safer way to bring your car to a stop than simply removing the engine power. Category 2 stop, also known as safe stop 2, is very similar to a category 1 stop, but the main difference lies in the final motor state. If you notice in the graphic on the right, once we get to our standstill, we enter 0 speed monitoring instead of safe torque off. Because of this, we can actually have improvements in productivity when needed, but the most important thing to remember is that a safe stop 2 or category 2 stop cannot be used in an emergency stop situation. This is still a good option to use if you need to bring your load to a controlled stop, and it may coast for a little while, but because of that end state, it does have an impact on the safety system. This is similar to using your brakes to bring your car to a stop, but then leaving the engine engaged once you reach a standstill. Now we're going to have another couple polling questions here that Andy is going to post for you.
Yes, we're going to post the second of polling questions here, and that is, what safety rating do you guys typically design to? I'll launch the poll now. For those out there who've designed safety systems. Okay, looks like just over half of us have responded. We'll give this a few more seconds for those out there still mulling this one over. Okay, looks like the responses have slowed down, so I'm going to go ahead and post the results of this. There you go, Chris.
All right, and that looks like what we typically see in an average day working around our customers is that most applications end up being PLD. We do have customers out there who aren't sure what they need, and we're always happy to assist you guys to figure out what you need to make sure you're running optimally. And then there is a small portion of applications we see that do reach PLE because of the hazards involved. But at the end of the day, most of the applications we run into are that PLD rating. Move on to our next question.
Okay, poll question 3 for everybody. Give me just a moment here. Okay, what's the difference between, what's the difference between category 1 and category 2? We'll go ahead and post that. Again, what's the difference between category 1 and category 2? Okay, we're a little over halfway through. Okay, about 3/4 of the way through the respondents. We'll give this a few more seconds, guys. Okay, looks like things have tailed off. I'm going to end the polling and we'll go ahead and share our results. There you go, Chris.
All right, thanks, Andy. So thanks for all your responses, everyone. Couple takeaways. Category 1 and Category 2 actually can bring the load to a stop in the same amount of time, regardless of which one you're using. Category 2 cannot be dry-based, but as we'll find out shortly, Category 1 actually can. But just to reiterate, the most important thing that I want you guys to take away from this is that Category 2 cannot be used for an emergency stop situation. Can be used to bring your load to a controlled stop, but only Category 0 and Category 1 can be used for emergency stopping. All right, so on to the next section on how to actually implement these safe stopping solutions. So we'll start with safe torque off, which has kind of evolved over time. Some of our drives, like the PowerFlex 523, still use an external solution for their safe torque off. You can see from the graphic here that involves working with external relays and external contactors. This adds a lot of panel hardware and a lot of extra wiring to a system that typically is nice to avoid if possible. But on some systems, if we only have one simple drive, this may be the best way to go about it. The next level of safe torque off that we offer is what we call our hardwired safe torque off. This is available on a lot of the drives we offer. You can see some of them listed below. And what this does is still uses those safety relays to interact with the safety devices, but instead of using external contactors, this portion is moved inside the drive to remove the power from the motor. This reduces hardware in the panel and also reduces setup time and configuration, lowering costs of implementing a safe solution. The newest option for safe torque off is what we call network-based safety, which uses our SIP safety protocol. You'll notice that this does require a red guard Logix CPU in order to work, but now everything is done over the existing Ethernet connection, which makes the setup a lot easier, removes panel hardware, and makes for a more flexible system. At the end of the day, the controller and drives may cost a little bit more, but your solution may actually cost less while being higher performance because of the lower install time and hardware involved. So just to touch again, you can see on the right here, we have what would be considered a hardwired system where we have a safety relay that is wired into the safe torque off connector on the drive. We have our dual channel outputs going to that connector. And on the left-hand side, you can see what would be just a little snippet of safety logic for doing the network-based safe torque off. This SIP safety protocol is all done through the controller, which means you have much more control over how the safety system actually works. It's only a few lines of logic and makes it a lot easier to troubleshoot and implement. So as you can see, implementing a category 0 or safe torque off solution is pretty simple, but what about the safe stopping that we've been talking about for category 1 and 2? So the first thing is we are going to need a little bit more hardware in order to implement our safe stopping. So the absolute minimum you're going to need is a guard logic controller, either the 5380 or 5580 controllers, and then either a Kinetix 5700 servo drive or a PowerFlex 750 series with the appropriate safety card installed. For recommended hardware, when we're using a servo system, we highly recommend a VP series motor with a SIL2 rated encoder built into the motor. We'll touch on this on the next slide, but there's a very specific reason why we recommend this, and it doesn't actually help increase the safety rating of the system. And then the last optional piece, which is based on the level of safety you need, which if you're going to PLE, you're going to need a secondary feedback device. You can use something like the SIP safety encoder shown in this slide. So for the SIL2 encoder, why would we recommend this over just using our standard encoders? Well, as you can see from the flowchart listed here, it doesn't really have to do with safety ratings as much as it has to do with the validation of the safety system. If you're using the safety rate encoder, all the testing and validation has already been done by the encoder manufacturer, which means it communicates to the drive that it's all the proper properties, and then you're ready to go. If you want to use a standard encoder, then you actually have to work with the encoder manufacturer to prove that it's suitable for use in a safety system. This involves calculating a lot of additional values and adds a lot of time and complexity. So for something that only typically has about a 3% added cost onto the motor, it's highly recommended that you use the SIL2 encoders in these systems. So as far as the drive, controller, and software, I'm sure you guys want to know what you can use. For the software, as long as you're running version 31 or higher of Logix, you're good to go. If you're using the 5580 or 5380 guard Logix controllers, you're good to go. And then with the Kinetix 5700 servo drives, you can either use the ERS4 versions, which support all of our safety functions, some of which we will touch on in a later webinar, or you can use the ERS3 versions, which have the networked and hardwired safe torque off, as well as drive-based safe stopping version 1. So when we're integrating the safe stopping into our controller, one of the important things to do is get all of the feedback devices into our safety logic. Any safety axis of motion that requires that a safety function be executed on it would require this safety feedback interface function to be used in the logic. The SFX function is used to convert feedback and position and velocity feedback from the safety drive into user-defined units for position and speed, and to define an absolute reference position. Though the SFX instruction is a safety instruction, it alone does not perform the safety function like Safe Stop 1 or Safe Stop 2. Note that because Safe Torque Off does not require feedback, the SFX instruction is not required when just implementing Safe Torque Off. When we're doing these safe stopping applications, one thing to note is that the instructions we're using in our safety logic are actually just monitoring instructions, and the safety and standard tasks need to be coordinated together. When the request is sent from either a door lock or a push button or a pendant, the Safe Stop 1 command begins monitoring and turns the active bit on. This bit is then passed to the drive, which then passes it to our standard logic to activate our motion command to begin the stopping of our motion. Need to remember that the safety task does the monitoring while the standard task is actually controlling the motion. This works the same for all of the safe monitoring functions, whether it's safe stop 2, safe limited speed, safe limit position, or one of the other options we have available. So now that we know what we need to integrate the logic, we'll talk a little bit more about the specific safe stopping instructions. A category 1 stop can actually be executed 2 different ways, a drive-based and a controller-based option. The drive-based execution can be done just by configuring the drive without actually having to set up the logic in the safety PLC. This is faster, however, it's fixed because all the configuration is sent and downloaded to the drive, and it only can achieve a SIL2 or PLD rating. With the controller-based option, we can get all the way up to SIL3 PLE, and it's more flexible because we are using the safety logic to control the instruction. This allows you to change your parameters based on loads and machine state to optimize your productivity while keeping the machine as safe as possible. Note that both of these options do still require a safety controller. For the drive-based integration, we have both monitored and time-based options available. The monitored option does require a little bit more setup, but as it sounds, it is monitoring the stop the entire time to prevent any hazardous situations from occurring. The time-based is much easier to integrate. However, it does not actually monitor the system. For the controller-based integration, as we saw before, we would use the instruction on the right in our guard Logix controller to implement the safe stopping. We do have both monitored and time-based options available in the controller as well, and this one instruction has all of the variables that are needed to control it. So what's the difference between time-based and monitored safe stopping? The time safe stop 1 is a safe stop function where a fixed amount of time is given for the drive to stop. The time-based function does not monitor the drive or detect a standstill. When the max stop time expires, safe stop 1 completes the transition to high, which activates safe torque off. Once activated, the safe torque off will operate as described in the section on safe torque off stopping function, which is configured in the drive. It can also be implemented with a hardware-based solution using time-based relays if you don't have a drive that actually supports safe stopping. A monitored safe stop 1 is a ramped safety stop where the motion safety instance monitors the speed ramp to a standstill. When the standstill is reached, then the motion safety instance removes torque from the motor. When active, the axis speed is monitored and must remain below the speed limit ramp. The axis motion control application must be coordinated with the safe stop 1 activation to bring the axis to a standstill speed without encountering any errors or faults. Integrating a category 2 stop is very similar to a safe stop 1, although there are no drive-based implementations for a category 2 stop. As you can see, once we get to a standstill that is detected by the driving controller, we enter our 0 speed monitoring. This allows the system to still have control and hold the motor position while ensuring that we are at a standstill in a safe way. So one of the most common questions I have is, what happens if there's an issue while we're doing one of these safe stoppings? Whether the motor runs away, something breaks, who knows what could happen. With a timed safe stop 1 application, nothing will actually happen if there's an error. The safety task does not have any feedback on the load, and the only thing we'll do is enter safe torque off once we hit the expired time. With a monitored safe stop 1 and safe stop 2, if a fault occurs, whether the motor speeds up and crosses that ramp rate or something else happens, safe torque off will immediately go active and there will be no more torque on the motor. This ignores any safe torque off delay that may be configured in the system. So the nice part with the monitored system is that if there's any issues, it'll default to a safe state to prevent any further hazards to the machine or operator. Now we talked a little bit about PLD and PLE solutions, but just to give you an overview, if you were to look at this using a full SIP safety system, which hopefully by the end of this year, we'll have some of these unreleased products available for a complete system, you'll notice that we have our compact guard Logix controller, which is currently only available in a SIL2 PLD rating, as well as our Kinetix drives, our PowerFlex drives, all of our safety IO devices right on the Ethernet network. Now, in those applications where SIL3 PLE is required, we do have to change things up a bit. You'll notice that currently we'll have to use a guard Logix controller in a control Logix chassis, which requires adding the second safety partner. And our servo system has a secondary encoder that is going back to the drive to allow for the dual feedback. We still have all of our other devices on the Ethernet network, however, allowing for quick and easy setup. With that, we'll have our last polling question from Andy.
Okay. Let me get that question up here. Give me just a moment. So polling question 4 is going to be what is the benefit of using a VP motor with SIL2 encoder? So what's the benefit of using a VP series motor with a SIL2 encoder? Okay, we're about halfway through the responses. Okay, we'll give this just a few more seconds for those who want to get their answers in. All right, looks like we got about most of you responding, so I'll go ahead and end the polling and post our results. There you go, Chris.
All right, thanks, Andy. Yeah, so as the majority you said, using a VP motor with a SIL2 encoder does greatly simplify the implementation of safe motion solutions. And as much as I wish it was the case, there is no one device that can guarantee a safe system. When you're designing safety systems using the information from your risk assessment, it's definitely a full system solution that requires proper controllers, hardware, and processes put into place. All right, and as we're starting to get to the end, we'll go over just a couple applications for using these safe stopping functions. So this first one is an example material handling or conveying application, where this one we have augers that are moving material for a certain process. Based on the risk assessment, is required that a PLE is required, and therefore a secondary encoder would have to be added to the system. When the operator pushes a line stop for the system, the line will ramp to a coordinated controlled stop using the Safe Stop 1 safety function for all 6 drives in the system. By using the controller-based system for this, it allows much more flexibility to control the stops based on what sort of materials or products are being run through the system. Depending on, with these augers, how compact the material is, how heavy, we may need to configure our stopping rates to be able to allow easier to move loads to stop faster while not tripping out the instruction on heavier loads that will take longer to stop. During machine changeover, based on the materials being processed, the line ramp rate can be changed by the operator using an operator interface. So this is something that can be automatic. You can have inputs, but you may also want to have different logic in an emergency stop situation, so that way if something does go wrong, you won't have to worry about overrides being in place that can cause further hazards. And because this is all done through logic, it can be done without modifying the underlying program, resulting in faster changeovers and improved efficiency. And our second example that we'll talk about is operator access to a registered knife. So in a situation like this, you've obviously got a very sharp knife working in the machine's process, but occasionally an operator will have to get access to that device, either to clear a jam, replace a blade, or take care of other maintenance. Using our Safe Stop To function, we can hit a request to enter, and using the safety logic, verify that the hazard is stopped and in a held position, which allows the operator to then enter the cell and access the knife without having to worry about the free mechanics spinning and causing further issues. So using our Safe Stop To function, it's not an emergency stop, but it's more of a process option that is allowing the process to be more efficient and less hazardous to the worker. And just to kind of tease some of the other functions, in addition to the safe stop we talked about today, there are a handful of other built-in safe stop instructions that are all TUV certified and built into the controllers. And if we combine these using our safety logic, we can actually perform additional safety functions such as safe cam, safe maximum speed, and safe home. Just to review what we discussed today, a risk assessment is needed to determine safety requirements of your system before anything else can be done. Safe torque off is the most basic and easy to integrate safe stopping function, but it's typically overused. Safe Stop 1 has both drive-based and controller-based options. Safe Stop 2 cannot be used in an emergency stop situation. Controlled safe stopping can improve productivity and safety while lowering overall production costs. All these instructions are certified by TUV, and the safety task does the monitoring while the standard task is what controls the motion. And with that, I will have Andy read off our Q&A submissions.
Yes, just a reminder for everybody before we get into the questions that were submitted in the chat. Today's presentation was recorded, and the presentation will be made available to all those who attended, for future reference. So we do have a few questions in the chat, and again, if you guys have questions when we go through, please, as a reminder, post in the chat window. I'm sorry, in the Q&A window. So your first question, Chris, is what about integrating a mechanical brake that engages on a time delay after a safe torque off condition occurs? Is this different from SS1 and SS2?
So basically, if I understand it correctly, what we're looking to do is after we've come to a standstill, we'd want to use a brake to actually hold the load in place. Yes, so in addition to the safe stopping instructions, Rockwell does have a safe brake control function as part of the guard Logix controllers, and you could do just that. You could, to make sure it's all in a certified safe system, you could use that safe brake control to control a brake in the system. So once you come to a standstill, if you want to remove power from the motor, instead of using something like a Safe Stop 2, you could use the safe brake control to hold the load in place.
Okay, our next question is, when using a third-party drive with a single-channel emergency stop input and a safety PLCIO, are external safety relays required, or can the safety logic be set up to achieve a PLD system?
Okay, so just to unpack that one, we've got a third-party drive that only has a single channel input on the safe torque off. and we want to use a guard Logix with, I'm assuming, a safety output to work on the system. I think, were they asking if we can achieve PLD with that?
Yes, I'll go through again. So using a
Okay.
third-party drive with a single channel emergency stop input and safety PLC IO, are external safety relays required, or can the safety logic be set up to achieve a PLD system?
Okay, I've got it now. I may defer to Mark to confirm this answer, but I believe we still need to go through a safety relay in order to have the proper safety system. Mark, I think you can explain exactly why that would be the case.
Yeah, you cannot achieve performance level D with a single channel input device. So that's number one. Can you hear me, by the way?
Yeah, we got you.
Okay. As far as once you get to either the safety PLC or the drive, from that part on, you will be able to achieve performance level D. But you would have to change the single channel emergency stop input to a dual channel to achieve PLD.
Okay.
Perfect. Thanks, Mark.
We got a couple more here, Chris. How do I calculate stopping times or decel rates?
So that's something that, it's basically just a basic physics equation. If you know how fast you're moving, how fast all your loading is, you can work that back through based on the torque available in the motor. This is something that can be done by hand, but if we're designing a new system, Rockwell has a nice motion analyzer tool that we can use to input all of our variables, and then we can use that to actually see, based on the motor performance, how quickly we can stop the load.
Okay. There's another one in here. Is there example code for how to implement these safe functions in a safety PLC?
Yes, so we have, for our labs at Horizon, we have played around with some of these functions, so we can give you some application code that you can take a look at, get an idea for how they integrate. Rockwell does also have labs that go over how to integrate these. And then for specific application examples, Rockwell has put together what they call safety functions, which those go through, they detail the hardware that's needed, the wiring that's needed, and the code that's needed to properly integrate the safety systems.
Okay, and our looks like our last question here is, how do we get more information on risk assessment or risk assessments?
Yeah, so if you're looking to get information on having someone come in to do a risk assessment, you could easily reach out to any of us at Horizon. If you know who your account manager is, they would be a great resource that you could give a call to. If you're not sure who they are or you haven't worked with them before, then you could reach out to myself directly, or give our main Horizon Solutions phone number a call, and we will make sure to get you to the right person to get you all the information you need on having a risk assessment performed.
Oh, we got another question that just popped in here, Chris. On an RTE requestum, can I use PLC output to unlock the door seconds after I know the drives are stopped, and be considered SS1? So on an RTE requestum, can I use PLC output to unlock the door seconds after I know the drives are stopped and be considered an SS1 condition?
Yeah, so that kind of sounds like, instead of using the official safe stop one function, we're essentially doing a time safe stop function. So what we could do is we'd have to have the feedback going through that safe feedback scaling, and then once you could use your Logix to set a threshold, which will then activate a timer to unlock that door 1 second after the motor speed reached that, which would, in essence, emulate a Safe Stop 1. As far as the certification of that safety system, that I am not sure on. I know Rockwell has gone through with TUV to certify that their functions are safety rated, and you probably just have to get some input either through a risk assessment service or working with us and Rockwell directly on making sure that that Logix is actually safe.
Okay. Any other questions out there, guys? We'll give you another minute to submit them. But until then, on behalf of Chris, Joe, and myself, we certainly want to thank everyone for joining us today. And to please be sure to visit Horizon's website for future webinars coming up. We do have a schedule posted up there, not only ones hosted by Horizon personnel, but also our vendor partners. So again, we thank you for your time today, and hope everybody has a good day.